Number 3 from section 5.1 says, is lambda equals 7 an eigenvalue of this vector? If so, find one corresponding eigenvector. Okay, well, remember, we say that lambda is an eigenvalue of matrix A if there exists some column vector x that satisfies this equation. All right. So let's see if we can satisfy that equation for lambda equals 7, if we can find an x that will satisfy that equation. So here's the equation. And remember, x is a column vector, so you could, I suppose, rewrite this thing like this. And that's kind of the trick. In general, you can rewrite the equation with the 0 column vector on the right-hand side if you do this little trick. And that I, of course, is the identity matrix. So essentially, I'm subtracting 7 from all of the main diagonal elements and multiplying it by x and trying to make that equal 0 for some x. So let's do that. So 5 minus 7 is negative 2. 2 minus 7 is negative 5. 8 minus 7 is 1. But all the other elements are the same. So is there a solution, x1, x2, x3 for this system? Well, we'll find out. So let's do the usual. And I'm going to do it with a calculator. So the calculator gives me this for reduced echelon form. And notice that it looks like we only have 2 pivot columns. So that means we have a free variable. So there are infinitely many solutions to that equation, which means there is more than just the trivial solution. You don't count the trivial solution as part of the definition, by the way. So this is only an eigenvalue if there's a non-trivial solution for x for that equation. And there is, because we have a free variable. There are infinitely many solutions. So let's characterize the solutions. So x3 is the free variable. So factor out the x3 as usual, negative 3, negative 1, 1. That's certainly one eigenvector. So it looks like it is an eigenvalue of this thing.